Let's see if this works. Okay, it does work. Good. So the first thing we need to do is talk about frame of reference. I mentioned it at the beginning of the school year as far as foundations. When we're talking about chemistry, we start out with the simple things, and then we built on those, and we built on those, until finally we came to the last chemistry test, and you're actually using your knowledge to not only predict products when you threw chemicals together, but also tell me how they're going to react and what ratio. Need something?
I'm waiting.
Okay. So, same thing with physics. Today, we're going to start out here with simple things like motion. And eventually, we're going to stair-step our way to the very top, and it's going to get more and more complicated. So, at any point that you don't understand what's going on, you need to take time to understand it before we get to the next step. All right? So today, it's pretty easy. Tomorrow, it'll be a little bit more difficult, and so on and so on. Okay? White, you have a question? All right. So today, we're going to talk about first frame of reference. And what that means is, if you're ever going to have motion, then you need to have it motion relative to something else. So, when you look in the morning, Miss Steele, you would say that the sun rises in the east, yes? Well, what's your frame of reference? How do you know it rises in the east? What's it rising compared to? Oh, no. How do you know it's rising? That's the question. That's the motion.
Well, it's moving against a different background.
And what's the background in this case? Okay, so she says sky. I would propose it might even be the earth. So it looks like it's rising. It looks like it's rising in the east, yes? So your frame of reference in this case is the earth, right? Relative to the earth. Or you could be using your new fancy Dan rollerblades. And you're skating down the road, like your mommy told you not to.
Street.
Right? Street, road, same difference. And you...
Pavement. Boulevard.
And you find that you feel like you're going pretty fast, right? And you pass the sign, you pass the little kid on his tricycle, and you're going faster than you. And how do you know you're going faster? What's your frame of reference? Yes? The little kid on the tricycle, right? You're going faster than the tricycle. The kid's going backwards, looks like, right? Compared to you. That's your frame of reference. How about this one? What if you are sitting in an airplane, and you look over at the snack tray, and you say, well, I'd like one of those Canada Dry ginger ales, please. And so they pour out some ice, and they hand you the drink, and then you set it down on your little tray. Now, how fast is that drink going?
Well, as fast
Yes?
as your hand. I think as fast as the plane is moving.
But it's just sitting there on your tray, Millard. If it's just sitting there and not moving at all, what's your frame of reference?
The ground. The sky. The plane. Oh, no, you don't
The
have
plane. So it's just sitting there not moving. But Millard, let's say instead you're standing by your house and you're watching this plane overhead and you see the drink going by. How fast is the drink going now? As fast as the plane. You know, some 600 miles an hour. That's pretty fast, though. So your frame of reference in this case is okay. You could say the background sky or background cloud, or you could even say the ground. So your frame of reference is the ground. The airplane seems moving relative to the ground, but to the person whose drink is right there on the tray table, it doesn't seem to be moving at all. So when we talk about motion, you always have a frame of reference. Most often the frame of reference is going to be the earth, but not always. Frame of reference is interesting. Like you go to Indianapolis Airport, and as you walk in from the parking lot, there are these little roller thingies, and they expand them out, and it looks like a moving walkway, right? So you get on the walkway, and you just stand there, and there's your suitcase next to you. Is the suitcase moving?
Yes.
Well, in relation to the conveyor belt thing, no. But in relation to the Earth, yes.
Right. So if you're here, your suitcase is here, and you're here, the suitcase does not appear to be moving at all. Right?
Neither does the
But if you compare the suitcase relative to the non-moving sidewalk, it does appear to be moving. Interesting.
Isn't everything moving because the earth is moving like?
Oh yeah, everything's moving. So, but how do we know that? You have to have some frame of reference. It's moving relative to something else. Okay? So that's the idea with frame of reference. Okay. So, everything is relative. And then another idea is... Oh, did we do this wrong again? And now it does this.
right on.
Oh, okay, we could try that. Resume. Let's see, does this clear it? Uh-oh, we're writing on that now. Uh-oh. Uh-oh. We got serious problems here. That's it.
No, it started over.
Start over?
No.
Okay. So let's try that. Alright. Now why is it not writing? Very strange. Okay. So when we talk about motion, we almost have to start out with distance. So distance is measured in a straight line from point A to point B. It's measured in what unit usually? In science?
Meters.
Yes. Meters. So it's measured in meters. Abbreviation is M. And so it adheres to all the SI conventions where you have the prefixes and suffixes. Usually we're just messing with the prefixes. So a kilometer is km. It's going to be how many meters, McNulty? 1,000 meters. Indy is not McNulty. McNulty, what about centimeter?
100th.
1/100th of a meter. Good. And so those are going to be our most common ones. Meters, kilometers, centimeters, that sort of thing. Can we do other things? Yes, of course, because it's all in the decimal system. So that's nice. So the distance just from here to here. Now, there's a difference. This is working. Okay, good. There's a difference between distance and displacement. Distance is just a point from one point to another. The distance is the measurement in between them. Displacement, on the other hand, adds direction, which makes it a vector. You guys heard of vectors before?
Yeah, just in like this.
What's a vector? Yes?
Wait, I know the difference between the displacement and
Okay, well, what's a vector? Vector? Yes?
This is something that goes array that goes in two different lines.
It's often used as array. Essentially, it's just a quantity with a direction. So any quantity we have that has a direction is a vector. So displacement is considered a vector because what it is its distance with direction. Alright? So we could say 50 miles, or we could say 50 miles east. Whereas 50 miles east is going to be our displacement. Yes?
So adding that east makes it a displacement rather than a distance.
Correct. So, how that works is you'll find out, here we could go, let's say we go from the lovely state of Indianapolis, yes? Right? Isn't that nice? So we're going to go up to here in Chicago, which is,
3 hours.
let's say 250 miles. And then we're going to go over here to St. Louis and see the arch.
Hey, that's where my uncle lives.
St. Louis, and let's say that's, 400 miles. And then we're going to come back to Indianapolis. Oh, let's see.
620.
Let's say 320 miles. I'm not sure the actual distance. But let's say we do that. So, using your math skills, what is the distance that we've gone?
970.
So we just say, okay, let's do 50 plus 320 plus 400.
970.
That's going to give us
970.
970 miles. Good. Now, on the other hand, what's the displacement? Well, displacement, by definition, is distance from your starting point. So, displacement is going to be 0, because you're right back where you started. Oh, that's kind of a little weird, isn't it?
Oh, I get it now.
It's like,
Yeah, distance and direction. So you started here and you ended up here. So when you run track, what's your displacement? All the time it is 0. It doesn't matter if you're doing the 100, the 200, the 400, the
well, the 100 you only
1500, 1600.
But I had the 100 you just go there. We're gonna laps.
Oh, that's true. It has to be a whole lap. So it has to be the 400 or the 1600 or the 800. Whereas the 100, you actually do some displacement, don't you? Okay. Yes.
So if you were to go in like a half square, then the displacement would be the diagonal, right?
Exactly. So, on the other hand, what if we just, okay, so let's go back to Indianapolis. Right? A little boot here. Let's instead go to South Bend and go console our poor Notre Dame people. Right? Yeah. Okay, and then from there we're going to go to Fort Wayne and pick up some of those fancy damn, what are those bags that are like all flowery and patterny? Bear Bradley. Bear Bradley, that's right. Not Bear Bradley. Bear Bradley. Bear Bradley. Oh, they look like teddy bears, they're so cuddly. So, we could say, all right, let's say it's, I don't know, 100 miles to Fort Wayne, 150 miles to South Bend. Obviously not to scale. So, what's our distance here? Going from Indianapolis to Fort Wayne. Yes?
150.
What's our distance?
Oh, 250.
We've gone 250 miles, right? On the other hand, what's our displacement?
Oh, I never thought we were Fort Wayne and
Right, in order to find displacement, you say, okay, it is from Indianapolis to Fort Wayne. Oh golly, how'd you figure out something like that? That is a vector, so it's got the quantity with a direction. So what would it be?
Calculate.
You'd have to calculate it, right?
Isn't it like the A squared?
That's exactly what it is. So you'd have to say, okay, this is A, this is B, this is C, right? A squared plus B squared plus C equals C squared, right?
Yes.
Yes. And so C is going to equal what? Quantity square root of A squared plus B squared. Oh golly. Right? So in this case, what is A? We can say it's 150. Square that plus
180.277.
100 squared. So what does that give us, Sokar?
180.2775.
But
Two,
we
right?
rounded to significant figures.
We rounded to significant figures, of course. And of course, we couldn't forget our units. So that's miles squared plus miles squared is going to give us, but the square root of miles squared is miles. So our displacement is 180.28 miles, let's say. We're not going to worry about stick figures on this particular problem since I said it was just 100 miles. Oh, it needs a direction. What is the direction?
Northeast.
Northeast.
North by northeast.
Good. North or north by northeast. Yep. So it has direction. So this is our displacement. And that's how you figure that out. So another example. Let's go back to our walkway, shall we? We're on our Indianapolis walkway. Right?
Yeah. Looks like a spaceship.
Yeah. Okay. So let's say instead of let's say you're walking let's say the walkway is going 4 miles an hour and you are walking 4 miles an hour.
Guys, some people look like that.
Right? Yes?
Yes.
Okay. So you would say after 1 hour, what's your distance that you've gone?
4 miles.
Yes?
16 miles. Right? Because you're going 4 miles an hour.
Oh.
Or is it 8?